Notice this video is the intellectual property of Ramesh Autar and is distributed under the trademark or logo Arrow Easy Learning as shown below. Significant figures. First, we will talk about the concept of significant figures. Then we will deal with identifying significant figures, working with significant figures. We'll also deal with rounding off numbers, and lastly standard form and or scientific notation. So let's begin with the concept of significant figures, and then we will look at those. If I were to ask you to add these two numbers, 65.7 and 0.0035, without the use of a calculator and to show your working, most likely this is what you would do. 65.7, 0.0035, you'd write them down like that with the points lined up, and then you would add them still with the points lined up, and that will be considered correct. Now if I were to ask you to add 65.7 kilograms and 0.0035 kilograms, you may be tempted to do the same thing. So you write it like this, and you give this here as your answer. Now CSEC will consider this answer here as wrong. At this point you may be wondering, okay, if this one is right and this one here is wrong, how come? Consider that you have a bathroom scale like this. This is the analog part that you are seeing. The digital part is here. We will put that in a little while. And I ask you, what is your mass? You may say, okay, if this is 60, this is 65, it's 65 point something, and the point something is close to 66. So you may say 65.7. You wouldn't say 65.1 because that will be closer to the 65 than to the 66. So you may say 65.7. The actual digital reading says 65.7. Assume that you stand on this bathroom scale and the reading says 65.7 kilograms. A mosquito of mass 0.0035 kilogram then lands on your hand. Now, what is the reading on the scale? Would it say 65.7035? Actually, it will say 65.7. And the reason for that is simply this. The sensitivity of this scale that you see here, digitally, it's 0.1 kilogram. That means that the least difference it can measure is 0.1. Now this mosquito is 0.0035 kilogram. That is much less than 0.1. Therefore, the mass of the mosquito will not register on this scale. The scale is not sensitive enough, and so it will still say 65.7. Now you get the idea why this here, why that is wrong. Truth of the matter is, the scale will not show this 0.35. That part will not show up. It will only show up to the 0.7. When we are dealing with measured quantities, we cannot treat them the same way as we will deal with pure numbers. We need to think in terms of our uncertain digit. So yes, as pure numbers, that will be correct, 65.7035. But when you are dealing with measured quantities, 65.7035 would be incorrect. Your answer is actually 65.7. If you write 65.7035 kilogram in CSEC, 1 mark will be deducted because you have too many significant figures. Consider further, if you have a box like this colored box, and you want to measure it, and I give you a ruler like this, all the calibration on the ruler is 0 centimeter, 10 centimeter, and 20 centimeter, and I ask you, estimate the length of this box. That is 0, this is 10, that is 20. What is the length of this box here? You can say 15 centimeters, and that is a very good estimate based on the ruler that you have. But if I give you another ruler, same box, and the ruler looks like this, at this point you could see 14 is here, you could see 15 is here, so it's not quite 15, but it is more than 14, and it is more than halfway past 14 towards 15. So you cannot say 14.1, that would be somewhere here. You cannot say 14.4 because remember you are like past halfway between 14 and 15. So you could say 14.6, you could say 14.7. You may be hard pressed to say 14.8 because that would be closer to the 15. You certainly would not say 14.9 because that is almost 15. So let us say 14.7. That is a very good estimate based on the ruler you have to measure. Now same box, but this time you have a ruler that looks like this. Let's expand this a little, and you can see that you have passed 14.5, 14.6. It is not 14.8 nor 14.9 nor 15. It is somewhere between 14.6 and 14.8. So where of this green line are we measuring? Are we measuring on the left of the green line? Are we measuring on the right of the green line? Are we measuring in the center of the green line? Can we say it's 14.69? Can we say it's 14.70? Can we say it's 14.71? We know for sure it's 14 point somewhere around 7. Maybe 69, maybe 70, maybe 71. Let's review that again. On ruler A, if we say 15 centimeters, that's here, we have an uncertainty of 1 centimeter, and you decide that if you are using an analog scale. And so on ruler A it could be anywhere from 14 to 16 centimeters if you look at this. But when you come to ruler B, we find that the situation is different. We now know it's more than 14, it's less than 15, it's somewhere between somewhere around 14.7. Now we are unsure about this 7. So we can say it's a 0.1 more or a 0.1 less. So it'd be like 14.6, 14.7, 14.8 based on that ruler. We haven't reached this ruler as yet, based on this ruler. So 14.7 plus or minus 0.1 means that it is anywhere from 14.6 to 14.8 centimeters. That is this measurement. Notice that this measurement is more precise than that one. But then when we come to this third ruler and we say 14.70, now it is this digit that we are not quite sure about. It could be a 0.01 more or a 0.01 less. As a consequence, when we say 14.70, we can mean anything from 14.69 to 14.71. actually much more precise. As you have uncertain digits more to the right, you become more precise. Over here we have that margin of error, here we have that margin of error, here we have that little bit margin of error. Now this is when you take measurement using an analog scale, you determine your margin of error. However, if you take a digital measurement, or if you are given a measurement, then based on the measurement we will work out the error. 10 centimeters, for example, means that you are not sure about this one, so it could be anywhere from 5 to 15. This one is in the tens position, so we take half of that position. Now if you say the measurement is 15 centimeters, now you are sure about that one. It's more than 10 and it's less than 20, but now you are not sure about this 5. Now remember, this is if you are given a measurement or if it's a digital measurement. Now if you take that measurement, you determine what your uncertainty is if you are using an analog scale. But we have a digital measurement, or we are given a measurement, we will assume that this 5 here is uncertain, and because that 5 is in the ones position, the uncertainty is really 1. So we take half of the position 1, more or less, and we get 0.5. So when we say the measurement is 15 centimeters, we actually mean it's 14.5 to 15.5. 15 plus or minus 0.5. If you say 14.7 centimeters, now you are sure of the 10 position, you're sure of the ones position, you're not sure of the 1/10 position, the 0.7. Now half of 1/10 is 0.05. Half of 0.1, which is 1/10, is 0.05. So your measurement that says 14.7 will actually mean 14.7 plus or minus 0.05, which is 14.65 to 14.75. And if you say your measurement is 14.72, so now you're sure of the tens position, the ones position, the 1/10 position, you are not sure of the hundredths position. So we will take half of that position, which is half of 0.101, and it's 0.005. So a measurement that says 14.72 actually means 14.72 plus or minus 0.005, and if you work that out, it would be 14.715 to 14.725. Consider further, if you have a number like this, 4,356.287. This number actually means 4,000 plus 3 hundreds plus 5 tens plus 6 ones plus 2 1/10 plus 8 100 plus 7 1,000. If you say that the distance of a village is about 4,000 meters, you're not quite sure exactly if it's 4,000. It could be a little more and a little less, but how little more and how little less is determined by what position this number is in. It's in the thousands position, so we will take half of the position, not half of the number, half of the position, which would be 500. So if you say the distance between two villages is about 4,000 meters, what you actually mean, it's 4,000 plus or minus half of the 1,000 position, which would be 500, and so it would be anywhere from 3,500 to 4,500. If you say 4,300 meters, you have a slightly different situation. Now you're sure of the 4,000. It is more than 4,000, but it is less than 5,000. What you are not sure about is this 300. It's somewhere around 300. Now, since this 3 is in the hundreds position, we will take half of this position, not the 3, the position. And so half of that position, half of the hundreds, would be 50. So when you say 4,300 meters, you actually mean 4,300 plus or minus 50. And so if you subtract 50 from that and you add 50 to that, you will get 4,250 to 4,350. Now, what about if you say, instead of 4,300, you say 4,350. Now you are sure of the 4,000, you are not sure of this 50, the tens position. So since that 5 is in the tens position, we will take half of this 10, which will give us 5, and our measurement actually now means 4,350 plus or minus 5. You will get 4,345 to 4,355. And of course, if you measure something that says 24.538 millimeters, now you're sure of all of these, all of these, all of that. You're not sure of that 8. And that 8 is in the thousandths position. And so if we take half of 1,000th, we will get 0.0005, and our measurement actually means 24.5375 to 24.5385. As you have uncertain digits in place values more to the right, the numbers become more precise. And this is what we are dealing with when we talk about significant figures. How precise are the numbers? Just to make sure you get the main point, consider these two numbers. And here I want to make the point that when we talk about significant figures in math or science, we do not mean that it has no meaning or is not relevant. Take these two numbers, 2,500 meter and 2,500 with a dot meter. In the first number, the 2 zeros are not significant. Doesn't mean it doesn't have any meaning. Whereas in the second number, they are. So this first number here, 2,500, actually means, since the hundreds is uncertain, it will be half of that 100 more or less. So it will be 2,500 plus 50 more or 50 less, which would be 2,450 to 2,550. That is this digit number here without the point. Now if you have the point, things are slightly different. What it means is now, instead of that number being uncertain, this number is now uncertain, and that number is in the ones position. So we will take half of the ones position and we get 0.5, and so 2,500 with a dot, with a point, actually means 2,500 plus or minus 0.5. In this previous case, it was plus or minus 50. Or 2,499.5 to 2,500.5. So this number here is more precise than that number. As you have uncertain digits in place values more to the right, the numbers become more precise. That is, the margin of error becomes smaller. Here our margin of error was 100, 50 plus and 50 more. Here our margin of error was 1, 0.5 more to 0.5 less. If you don't understand this fully at this time, you could listen to it again, but don't let that put you off. You can still do the work that follows, and by the time we finish the next 3 parts, you will understand this idea of significant figures. So the concept of significant figures, it has to do with precision. Next we talk about identifying significant figures, working with significant figures, and rounding off numbers and standard form.